Hey everyone. So I wanted to work through some examples and some computations that were related to the homework that I asked you to do this week. And one of the first things that we're going to look at is how to compute a Fourier coefficient from the integral. And we should keep in mind that we can do that basically for any function that we write down, we can compute Fourier coefficients for. So as an example, let's start with kind of a weird looking function, which is the function f of t is equal to t squared. Now this isn't a parabola like the way we're thinking about it, because we're thinking of t squared as a function that is periodic on the interval from 0 to 1. And so we can think of this as a periodic parabola. And what a periodic parabola would look like if we plotted it was, well, it looks like the parabola from 0 to 1, but then it repeats itself because it's supposed to be a periodic function. And so between 1 and 2, we're thinking of this as a function that does this pattern again. And between 2 and 3, it does this pattern again. So as a periodic function, this is going to have a Fourier series that approximates it. So I could compute some Fourier coefficients for this. So one thing I might think to do would be, well, if I can express f of t as a Fourier series, then I could write down an expression that computes f hat of n, the nth Fourier coefficient, as the integral from 0 to 1 of t squared e to the minus 2 pi I n t dt. And I don't have to pick a specific value of n. I could pick a specific value of n, but I don't have to. I could do it for all n simultaneously. When you're trying to find a formula for the Fourier coefficients of a given function, a lot of times we do work with the formulas in terms of n instead of in terms of specific numbers. And then oftentimes what will happen is there will be a pattern that emerges in terms of which coefficients survive and which don't. So let's actually compute this. If I want to do the integral from 0 to 1 of t squared e to the minus 2 pi I n t dt, I have to use my knowledge of methods of integration. In this case, because there's a t squared in here, I'm going to use integration by parts, which is not going to be required, at least on problem 2. I think you should see integration by parts along these lines in problem 3, because you're going to get terms that look like t times e to the minus 2 pi I n t. So I'll do integration by parts. And integration by parts requires a piece that you differentiate and a piece that you integrate. I'm going to use a version of this called the table method, where I'm going to start with t squared. These are going to be my u's that I'm going to differentiate away, 2t to 0. And on the other hand, I have my complex exponential, e to the minus 2 pi I n t. If you integrate that, you get 1 over minus 2 pi I n e to the minus 2 pi I n t. If you integrate that again, you get 1 over minus 2 pi I n squared e to the minus 2 pi I n t. And if you integrate that again, you get 1 over minus 2 pi I n to the third e minus 2 pi I n t. And the way that this works is when you're doing integration by parts, with the table method, you just multiply across. And so this integral is going to turn into 1 over minus 2 pi I n t squared e to the minus 2 pi I n t. That's these two functions multiplied together. And then I subtract the next two, so minus 2t over minus 2 pi I n squared e to the minus 2 pi I n t. And then finally, I'm going to add these two together. And I'm going to get 2 over minus 2 pi I n to the third e to the minus 2 pi I n t, all evaluated from 0 to 1. Pretty standard integration so far. The only Fourier series we've done The only Fourier series we've done was remembering that the formula for the nth Fourier coefficient was given by f of t e to the minus 2 pi I nt. When you plug in 1, you're going to get a lot of numbers that look like e to the 2 pi i's. So here's a big important fact. E to the 2 pi I is 1. And it's 1 because it represents this point on the unit circle. And that's the point 1 plus 0i, which is 1. E to the I pi represents this point on the unit circle. And that's the point minus 1 plus 0i. So e to the I pi is minus 1. Now, not only are those formulas true, but any number of rotations around the circle preserve the equation. So this is also equal to e to the 2 pi I plus 2 pi k. And what that means is that if you have e to the I pi times any even number, you get 1 out. In this case, you're going to get e to the I pi plus any number of rotations around the circle. When you simplify this one, what you end up with is e to the I pi times 2k plus 1. And this number is odd. So e to the I pi times an odd number is equal to minus 1. Now, why does that matter for the problem we're looking at? How these numbers behave. So we're going to use that fact when we start plugging in 1s and 0s to these things. You notice in this question that we have e to the 2 pi I nt's all over the place, which means that the number that's inside the exponent is an even number no matter what. And that means when we put in a 1, we're automatically going to get a 1 out the other side. So let's rewrite this. T squared over 2 pi I n e to the minus 2 pi I n t minus 2t over 2 pi I n squared e to the minus 2 pi I n t plus 2 over 2 pi I n to the third e to the minus 2 pi I n t evaluated from 0 to 1. When I put a 1 in to each of these exponentials, I'm going to get a 1 out because e to the 2 pi I n is always an even number up there multiplied by the I pi. So this is equal to minus 1 over 2 pi I n minus 1 over 2 pi I n squared plus 2 over 2 pi I n to the third. Now when you put in the 0, what's going to happen is these terms are going to vanish. And so what you end up with is just this term left over. And so you have to subtract off 2 over minus 2 pi I n to the third. These terms are going to cancel because they have opposite signs. And when you're finished, what you end up with is a formula for the Fourier coefficients that looks like this. And this is typical of a type of function where you can actually do the integral, that you get these patterns out in the Fourier coefficients. In fact, if you like, you can simplify this into a single fraction if you like using a common denominator. But the idea here is that this is the pattern for the Fourier coefficients. If you tell me n, I could write down the Fourier coefficient for that term in the Fourier series. So this sort of exercise where we started with a function and we wrote down a generic integral for the Fourier coefficient, and then we solved it and got a formula. This is the same exact thing that I want you guys to do in problems 2a and 3a. Start with the function, write down the Fourier integral for the coefficient, solve it in terms of n, and then notice something about the way that the pattern works for different values of n. So let's do one last example of computing a Fourier series for a periodic function. And for this one, let's look at the sawtooth wave. So the sawtooth wave, or one of the sawtooth waves, looks like this. So we go just a straight line from 0 to 1. So f of t is t. And we call it a sawtooth because it looks like the blade of a saw. So this function is defined to be f of t is equal to t. That's it. Let your voice drop. There's a sawtooth wave. So again, as in problems 2 and 3, if we want to compute the Fourier coefficients for this, we could write down that f hat of n is equal to the integral from 0 to 1 of t e to the minus 2 pi I n t dt. So this one's actually easier to do by integration by parts because the table is going to be really short. T, 1, 0 for the u's and for the dv's. E to the minus 2 pi I n t minus 1 over 2 pi I n e to the minus 2 pi I n t. And 1 over 4 pi squared n squared with a negative in front of it, e to the minus 2 pi I n t. Construct your terms. This is a plus, this is a minus, and so you end up with the integral. And so you end up with t over 2 pi I n e to the minus 2 pi I n t evaluated from 0 to 1 minus, which is really a plus, 1 over 4 pi squared n squared e to the minus 2 pi I n t evaluated from 0 to 1. So what you end up with is 1 over 2 pi I n times 1 minus 0 plus 1 over 4 pi squared n squared times 1 minus 1. So that term vanishes. And all you're left with is 1 over 2 pi I n, which you could rewrite as minus I over 2 pi n. This is the general formula for f hat of n for the sawtooth wave. Now, the only case that we didn't get to, or that we can't do this for, is the case where n is equal to 0, because when n is equal to 0, this exponential isn't actually even here, and all we're doing is we're computing the integral from 0 to 1 of t e to the 0 dt, which is just t squared over 2 from 0 to 1, which is 1/2. So f hat of 0 is 1/2. And that makes sense, actually, because f hat of 0 always just represents the average value of f on the interval from 0 to 1. So the zeroth Fourier coefficient just establishes what the average of the function is. And then what the Fourier series is doing is thinking of the rest of the function as oscillating around that average value. In electronics, this is called the DC component. So if we think about the Fourier series as measuring a current moving through a circuit, the zeroth Fourier coefficient just tells you what on average the current flow is that doesn't alternate. All right. So what I write down in the end? Well, f hat of 0 is 1/2. F hat of n is equal to minus I over n pi. And there's a 2 down there. And if you wanted to start writing the Fourier series down from the formula, well, you could start by writing down the 1/2. Remember, that goes with the n equals 0 term. And then for n equals 1, if you put a 1 up in here, you get minus I over 2 pi e to the 2 pi I n e to the 2 pi t. And if you're going to put the 1 term in, you should put the minus 1 term in as well, which is just the complex conjugate of this, positive I over 2 pi e to the minus 2 pi I t. You could put in the n equals 2 term, and that looks like minus I over 4 pi e to the 4 pi it, and its corresponding negative term, minus plus I over 4 pi e to the minus 4 pi it, and so on and so forth. The point with the Fourier series is that it goes out in both directions. You can be as accurate as you want by continuing to add more and more terms to the outside. Okay, so having a formula for a Fourier coefficient actually gives you a very quick way of constructing the Fourier series. And many of the most useful functions in applied math and physics and engineering have very easy formulas that we can write down that determine the Fourier coefficients. As an exercise that's not in the homework, you might think about seeing if you could write down f hat, that is the Fourier coefficients for f of t is equal to t, f of t is equal to t squared. Those are the examples I already did. See if you could figure out how to do it for the function that looks like this. So here's 1, here's 0, and let's have the function go like this. Right away, you should be able to see that f hat of 0 should be 0 because the average value of the function on any one period is equal to 0. There's an equal amount of area up here as there is down here. So this function is going to look like f of t is equal to 2t minus 1. So try that one. So practice these. Computing Fourier coefficients of basic functions is one of the core ideas of working in applied mathematics and in all the various fields where that's used in. And there's a reason why engineers and physicists and applied mathematicians choose the family of functions that they do to use. And it's not just that they're physically awesome, it's that they're amenable to approach with this sort of mathematical understanding. All right, practice hard and I'll talk to you later.